Alrighty, what's going on, my friends? As always, no matter where you are, I hope things are going fantastically well for you. Now, my name is Dr. Jason Dinsmore, aka the OChem Whisperer, and I want to help you succeed in your organic chemistry class. Now, what are we going to be specifically talking about in this lecture? So what I want to do is show you how to work through synthesis problems, all right? Now, as I've mentioned before, and I think the last video we did synthesis, is I want to let you know that I'm going to go a little faster than I normally do. I know I talk fast anyway, I get it. I always try to slow down. But I just get so excited knowing that you all are going to crush your organic chemistry class. But I do want to let you know this one's going to go a little faster pace, because if you're working on synthesis problems, and I'm assuming the fact that you're familiar, at least semi-familiar with the reactions in organic chemistry, and now you're just trying to put them together. All right, so cool. Let's go ahead and do this. So this is the synthesis that we're going to work on in this lecture, okay? And so you can see that we start with an alkane and we wind up going to another alkane. So in this case, we can see that there's really no functional groups that stand out. It's just basically an alkane going to an alkane. So there are two key reactions that I'm going to show you in here, and how to form carbon-carbon bonds that are going to be incredibly important. And it's going to depend on where you are in your class in terms of if you're going to use them or not. Don't worry, I'm going to explain what that means here in a minute, okay? The first thing you always want to do when you're doing synthesis is number your carbons, because it's very easy to lose track of things. And I would recommend numbering everything through your entire synthesis until you become incredibly, let's say, what's the word? Comfortable with knowing where everything is, okay? So if we were to number our carbons here, and it doesn't matter which way you number them, you don't have to number them in the IUPAC form, just make sure you know how many there are and keep it consistent throughout the synthesis. We can see here that we start with 3 and now we have 4. So we've added a carbon, which means we formed a carbon-carbon bond, and there are two key ways that I want to show you that we need to be thinking about, okay? That are kind of, you want to kind of keep in mind. So let's go ahead and start, all right? So I'm going to go ahead and put the reaction up top so we can kind of keep track, and that's what's great about synthesis. You can always refer back to where you're starting and where you need to go. So as you're doing the synthesis, if you ever get stuck, go back and figure out, I need to go here, now how am I going to get there? Okay, it's nice. It's kind of like a roadmap that's always there. So let's say you have to start with an alkane. The number one reaction that I want all of you thinking about if you have an alkane is I want you thinking of a bromination, okay? And I realize that I left one reagent out, so if you're writing this down, I want you to do BR, and then below that arrow, I want you to write light, or I want you to write heat. You may also see H nu, I think it's called nu, I think that's what it is, or you'll see a delta sign. It means light or heat. So that's the other reagent, quote unquote reagent that I forgot to put on there, that I need you all put on there. That is the best way to start with an alkane, and start with, when you have to start with an alkane, is to start building molecules. Because now you have an alkyl halide, there's a lot of things that you can do with that. The next reaction that I want you thinking about, once you do that, is I want you to go alkane, and I want you to write this down, alkane to alkyl halide to alkene. That is a very simple synthesis to start getting a function group that is incredibly powerful and allow you to build a lot of things. Because we know with alkenes, ENE, you can do all kinds of reactions with that. So this sequence right here is incredibly powerful and will allow you to build a lot of different molecules. Okay, maybe not every single synthesis you're going to get to use these, but a majority of them. This sequence right here is going to be incredibly powerful. If you can halogenate and use that, or if you can form an alkene, even better. Okay, so we're going to go alkane to alkyl halide to alkene. All right. And so from the alkyl halide to the alkene, that's just a simple E2 elimination. I'm using a bulky base just to eliminate any SN2 that we could potentially get. So in this case, I'm using potassium T-butoxide, and we wind up getting our double bond, okay? So now we want to refer back up. We can see we have an alkene. We want to go to the alkane, and we also have not added a carbon yet, okay? So one of the first ways that we're going to be able to add a carbon-carbon bond is with an alkyne, and that's a terminal alkyne specifically. If you're not sure what a terminal alkyne is, you can go ahead and refer back to one of the previous lectures when I talk about that with my, I think it's the Introduction to Alkynes, talk about what a terminal versus an internal alkyne is. But that terminal alkyne H, it's acidic, and we're going to be able to use that to form our carbon-carbon bond, okay? So now what we want to do is we need to take this alkene and we need to turn it into an alkyne. So the way we do that is we do a bromination. Now I want to point out, and that's why I said in that first reaction, that's Br2 when we did our alkane to alkyl halide, that's Br2 light or heat. This one right here is just Br2, okay? So we're going to take our alkene, we're going to treat it with Br2, and that's going to give us a bromine on both sides, the dibromide compound. We don't care about the stereochemistry in this way, but if you are interested, it always gives you trans, all right? So we get the dibromide here, and now we're going to take this dibromide and we're going to do a 2 E2 eliminations back to back with a strong base, and then we're going to wind up adding a carbon group. Okay, don't worry, I'm going to walk through this, but we can see this NaNH2 is a standard base, a standard strong base that you are going to use with the dihalide to wind up getting the alkyne, the triple bond. And then that CH3Cl, that's just going to be the carbon addition that we're going to do here. Now let me show you what's going on here. If you take a dibromide like this, with NaNH2, which is strong base, what that is going to wind up doing is doing a double elimination. So you're going to get one double bond, and then you're going to quote unquote get another double bond, which would give us 3 lines, which would give us a triple bond. Now the thing about this is that NaNH2, like I just said, if you have a triple bond, a terminal alkyne, and you have a strong base, it will pull off that terminal H. And that's what it's doing here. So you can do this all in one shot when you have the dibromide and you treat it with NaNH2. Not only will you get the triple bond, but it'll also, in the same time, it's called in situ, meaning at the same time in the whole thing, will pull off that hydrogen, giving you a negative charge. Now what's great about this is we have the negative charge and we need to form a carbon-carbon bond. So usually when you think about this, you got a negative charge, you can do a substitution reaction. So if you have an alkyl halide, CH3Cl in this case, we can do an SN2 reaction and add our last carbon. So now we can see that we've got 4 carbons. I did not number them here, but I want you numbering them, particularly with alkynes. Alkynes, it's very easy to get lost in terms of the number of carbons. You want to remember there is a carbon on each side of that triple line. It is not just carbons on the outside. There is a carbon on that line on the outside. There is a carbon on each side of the triple bond, and then there's another carbon on the other side. So we've got 2 methyls and a triple bond, which gives us 4. All right. Now what we need to do is we can see we've got all of our carbons. We can refer back up to our little map there. So now we just need to go from the alkyne to the alkane. I get the alkene, alkyne, all those suffixes all mixed up. So what we're going to do here is a standard hydrogenation. So we just do H2 palladium on carbon. That's going to go all the way down to the alkane. We don't want to use Lindlar's catalyst because that will stop at the alkene, and we don't want, and that'll give us a cis alkene. We don't want to use a dissolving metal like sodium and ammonia because that's going to give us a trans alkene. We want to go all the way to the alkane. See, I keep getting that suffix mixed up. Alkyne to alkane, we just use a standard hydrogenation, all right? Now that's one way that you can use this, and the reason I use this one first is because if you haven't gotten very far along in, let's say, Organic Chemistry 2 or Organic Chemistry 1, depending on your professor, this one should work in terms of being able to build, just alkane molecules, okay? Now, if you've gone a little bit further and started talking about alcohols, I'm going to show you another way we could build this exact same molecule, okay? Now check this out. What we're going to do is we're going to do the same sequence. We're going to do alkane to alkyl halide to alkene, okay? So halogenation, once again, that should be light or heat below that arrow. Put that in if you haven't. Bromine, light or heat, because it's a radical bromination, gives us the alkyl halide, which on the most substituted carbon, because bromine, we want to remember, is brominations are more selective than chlorinations, so that's why I use bromine. And then we can do a standard E2 elimination with this base with an O-, and which gives us a double bond. So we saw that before. Now what we're going to do, instead of doing our dibromine and forming our alkyne, we're actually going to form an alcohol, okay? So in this case, do you all remember what this is? This is a hydroboration oxidation reaction. It gives us an anti-Markovnikov addition of water across the double bond, okay? So we can see that we're going to get our OH on the least substituted side. We're going to get our H on the most substituted side, okay? Now, does anybody remember how you make the Markovnikov addition of water across the double bond? I'm not going to say it here, but I just want you thinking about that and see if you can figure it out, or if you don't, go ahead and look it up, just to re-familiarize yourself with some of these reactions, because they're going to be important when you start doing a lot of synthesis, just to remember these, okay? And remember I said alkenes are an incredibly important functional group to be able to do synthesis, okay? So we're going to do our alcohol. Now what we're going to wind up doing is I'm going to show you how we can do the second way to form a carbon-carbon bond. The first way we talked about was having a triple bond, a terminal triple bond, terminal alkyne. We pull off that hydrogen, and then we can do an SN2 with an alkyl halide. Here what we're going to do is we're going to form a carbonyl group, okay? So in this case, I'm going to use PCC, and that's going to take our alcohol to the aldehyde. Now, if you haven't gotten to alcohols and you haven't gotten to these oxidation reagent stuff, don't worry about it, okay? You're going to go over it. I'm going to go over it later on. But if you have gotten there, this is just a really simple way of now taking your alcohol to the aldehyde, and now we've got another way of forming a carbon-carbon bond, okay? Now, for those of you that have gotten alcohols, the reason I'm using PCC is because I want to stop at the aldehyde. I don't want to go all the way to the carboxylic acid where if I used a chromium reagent, something like that. I want to stop at the aldehyde because it's much easier to work with that in terms of doing carbon-carbon bond formations, okay? So now that I've gone from the alcohol to the aldehyde, what I can do now is if I take a Grignard and I treat that with an aldehyde or a carbonyl, or let's just stick to an aldehyde here. If I treat it with an aldehyde, I can wind up forming a carbon-carbon bond, and if I follow that up in the second step with just water, I'll protonate that oxygen that's O- in the first step with the mechanism, giving us a new alcohol here. And now you can see I've got all 4 bonds that I need in my final product, all right? So that's another way we can form carbon-carbon bonds. The first one is taking an alkyne, deprotonating the terminal hydrogen, adding an alkyl halide. We can also take here a carbonyl, specifically an aldehyde. We can treat it with a Grignard followed by water, and that will give us a new carbon-carbon bond, all right? Now what we need to do is if we refer back up, we can see that we've got our 4 bonds to carbon, but we have an alcohol. We don't want an alcohol, we want an alkane. So we have to get rid of that. So what we're going to do is a 2-step procedure. We're going to treat that alcohol with H2SO4 and heat, And do all of you remember when you see heat, what does that mean? There's a big tip off when you see acid and heat together. You all remember it's an E1 mechanism, okay? So we're gonna wind up getting an E1 elimination. That's gonna give us an alkene. And then in this case, if we just followed up once again with another standard hydrogenation, we're gonna go all the way to the alkane, all right? So hopefully these two syntheses right here will kind of give you a really good idea in terms of how to think about building molecules. You can see the first one was a little shorter, this one's a little longer, but there are multiple different ways. So what I'd recommend doing is asking your professor or your friends, or going online and finding problems that are already worked out so you can watch the sequence, and then find other problems that are worked out and see if you can work them out yourself, and then refer back and see if you got the answer right or if you got something similar, and then see if you can find problems that don't have the right answer and work through. Because the best thing you can do with synthesis is just start working problems. Don't worry about it at the beginning if you get them wrong or you're not sure to. Just start drawing things out and find somebody that you trust, that you can rely on, that you can refer back and say, hey, how does this look? Whether it's your professor or a friend or somebody you feel comfortable with, show them, because the best thing to do is just practice, practice, practice. So by the time you get to your exam, you're an absolute OChem rock star. All right? So with that, thank you all so much for coming on here, and until next time, I hope you all have a good one.